Okay, so we're going to do completing the square and inverse of quadratics. Very first thing we're going to do is work on completing the square. So what completing the square is going from this form here. This is standard form. Okay, standard form of a quadratic. And essentially, and I'm going to move that down, what they mean by standard form when they see it is essentially you have y equals ax squared plus b at x plus c. Have you seen that before? Yeah. Okay. So this is our standard form, and in standard form, it's tough to graph. We don't really know where to put things. When you're factoring, you're going from standard form to factor form. Now what we're doing is working on going from standard form to vertex form. And vertex form is y is equal to, we have ax minus h squared plus k. Or, sorry, do you use h and k when you do this? Or do you guys use c and d maybe? Do you use h and k when you talk about this? The only reason I ask is because, right before we get to completing the square, I'll just do one other one. Vertex form with quadratics can be related to this, where you guys do, and I remember you doing this before, function of k, x minus h, and usually it's written like this, a for vertical stretches, k for horizontal stretch, c for translations, and d for vertical translations. And pretty much why the reason I ask you to use C and D or H and K is because these represent the exact same thing. The only difference is this form here means you can do it to any function, and this is just specifically vertex form of a quadratic. Okay, so there's similarities between them. Anyways, the goal of completing the square is going from standard to vertex form. Okay, so that we can see the vertex. This H and this K actually represent what our vertex is going to be, exactly where it is of a quadratic. So we're going to do that right now. What we do is first of all, we look at the very first two terms, so the a and the ax squared and the bx. And what we're going to do is we divide the first two terms by whatever our a function is. And in this case, our a variable, sorry, not a function, but our a variable is 4. So we take it out like a common factor, okay? So essentially we get 4 comes to the outside, and then we're left with x squared minus 6x plus 31, okay? Now from there, we kind of have a new b, you could say. Our old b was negative 24, now we're working with negative 6.
So you wouldn't take out 4x, which is...
We just take out the 4. We just want to take out the 4 in this equation. Okay? We don't want to take out the x. You're right, x is a common term there, but we're just looking to take out the 4, whatever coefficient is in front of our x squared. Okay. Now what we're going to do is we take this term and we consider it to b, and we put in a little equation that looks like this: b divided by 2 squared. It's like a side calculation we do. Okay. So what we do then is we take our term is, you could say it's negative 6. Okay. So negative 6 divided by 2, and then we square it. Well, what's negative 6 divided by 2?
Negative 6.
Yeah, and then squared.
No, 9.
Yeah, just 9. Now, 9 is what's important, and technically, we're looking for plus m minus 9. And the reason we're going to do this is what we're going to do is we're going to add and subtract 9 inside of this bracket here. Okay, so I'm just going to move this over just a little so we can fit it. 4x squared minus 6x. Now, here's the thing. I'm going to add 9 and subtract 9. Now, that's like adding what number? If I add and subtract 9? Nothing. So it's like I've done nothing to the equation. The goal, though, is what we're trying to do is we're trying to create a perfect square trinomial. Okay, and we'll talk about what that is in a second, too. So I've added and subtracted 9. Now, I actually only really need the positive version here. So I'm going to take the negative to the outside. This negative 9 is going to come to the outside of the equation. But in order to go to the outside of the equation, we actually have to multiply by our a factor. We've got to multiply by 4 when it comes outside, okay? Because technically, this 4, according to the distributive property, has to go into every term, right? So if I'm taking something out, it needs to be multiplied by 4, in this case, for those brackets to go off. So our next line is going to read 4x squared minus 6x plus 9. What's negative 9 times 4?
Negative 56. Negative.
You're thinking times 6.
Negative 6.
30. Yes, that's it. Negative 36. So negative 9 times 4 is negative 36. And we still have our plus 21. Or sorry, 31. Okay. Now, let's just equate what's on the outside here. Negative 36 and positive 31. What's that going to give us?
Sorry? Oh, plus 31, negative 5?
Yeah, that's right. So we have negative 5. Okay. Now, we're getting close to vertex form. Okay. If we kind of take a look here, this is like our A, and this is like our K, like I said. The only thing is our squared is in here. It's not out here, and we don't have an H yet. But what we're going to do is we're actually going to factor these brackets. Now, I'm going to show you how to properly factor them, but if you follow this process, there's a very quick way to factor it, and it will always work. So I'm going to do a little calculation in the middle here. Okay. So I'm going to take what's in here. I'm just going to focus on x squared minus 6x plus 9. Okay. So I take the factors of the first term, which are 1x and 1x. Factors of the last term, 1, 9, 3, and 3. And their product has to add up to equal negative 6. So what are we going to use?
3,
Yeah, that's right.
but negative 1 of them?
Actually, both. Right? If both are negative, when we add them, we're going to get negative 6x. And negative 3 times negative 3 will give us our positive 9. So what we're going to end up with is, in each bracket, x minus 3 times x minus 3, right? How can I simplify that or represent it another way?
X minus 3 squared.
Yeah, that's what's key here. I'm going to go up just a little so you can see this. So I can simplify this by x minus 3 squared. So when I factor this part here, the factored form is just x minus 3, right? I'm just going to put that down here. Just like this. So you can kind of see what we're doing. So, essentially, I can replace what I've highlighted there with what we have down here. Because this is equivalent. Squared minus 5. So if you notice, I replaced this big bracket by the factored form. Right? Now, this is exactly vertex form. We have our x minus h squared plus k. So we have an a value, which is our a. We have an h value right here. And we have a k value. Right? So we are now in our vertex form. I'm going to show you the fast way to factor this. The process, we really don't need to go through this whole process for factoring. What we've done is we've actually created what's called a perfect square trinomial. So the fast way to do this is if I just square root x squared, so we find the square root of x squared, and find the square root of 9. Okay? What's the square root of x squared? Yeah, plus or minus x, but we're going to go with the positive version. And for 9? 3. So what that means now is I just take the x and the 3, and I plug them in as the first and second term. And whatever sign is in front of this, our negative 6, I put down there. So had it been a positive sign, I would have brought down a positive. But because it was a negative, I brought down a negative. So we have x minus 3. That's the fast way of factoring all this. And we'll do another example so you can see it, okay? So this would be the entire page of completing the square. There's quite a few steps involved with this. Okay.
So I'm assuming, yes, I'm guessing that since there's no number, it just goes into bracket.
Yeah, that's right. So normally we would divide by what's in front of it, right?
Right.
Because there is no number, we can just put it right into brackets. So
So it would go,
there you go.
okay. And then you would go, x minus 4x bracket squared.
Okay, so you chose to just divide this guy by 2?
Yes.
Okay, so you called him the b, and you just divided him by 2, because that
Right.
will give us what's our bracket supposed to be. That's right. So then we're left with x after. Yeah. Okay. And then what did you say? So you did x.
X minus 4 x bracket. Alright.
Shouldn't be an x in here.
Oh.
So let's hold on. Let's not jump too far ahead. Let's actually do it the way we were talking about with this b divided by 2 squared. Okay. Our new b is the 8,
Yeah.
just so we can find out the other term. Okay. So we won't jump too far ahead.
Okay.
If we plug the 8 into there, what would happen?
It would turn into 4.
Yep. Which then turns into what's 4 squared?
12. I mean 16.
Yes.
Yes.
So 8 plus minus that. So we still keep that bracket the same. Minus 8x. And what are we going to do? We're going to
Add.
and
Subtract.
that's 12. Now what's the next step?
You move the negative 16 off to the outside.
Okay. What do I have to multiply it by when it comes out?
A, but there's none.
Well, technically, what's the...
Okay, there's technically a 1.
Yeah. So we multiply by 1. Is that going to change anything?
No.
No. So now what's my bracket going to read?
X squared plus 8x plus 16 bracket. Minus 16 plus 12.
Good. Okay. Let's equate on the right side. What's over there?
So that would be negative 4.
Now, here's the shortcut. Instead of working out all the factoring, I told you, the reason I showed it to you so you can see it proven, but here's the fast way. We've created what's called perfect square trinomials. So I just square root the first and last term, square root 16, and we're going to get x and 4. And the next line just reads the one bracket squared. This guy will be my first term, the square root of him, and the second one will be my second term. So we'll put them in like that. So what's the square root of x squared?
X.
Yeah, square root of 16.
4.
And what operation do I bring down?
Negative.
Yeah, because it's a negative in front of the 8x. So we get negative 4 and then minus 4. So that's the fast way of doing it instead of doing all the factoring there. Okay? Okay, so the last one we're going to show you is we're going to try to go through this the quickest way possible. Now this does have an a value. Okay, so again, we are going to divide by whatever the a value is, okay, which is negative 5. We're going to take it out almost like we would a common factor. So the negative 5, we'll do it in red, comes to the outside. It's now our a in vertex form. And left with x squared minus 2x, okay, plus 35. Now, here is the little equation where we can pretty much jump to the second last step from here, okay. This equation, reference to this, and we still do the b divided by 2 squared, but we're also going to multiply by, I'm just going to change the color so color coding. We're going to multiply by negative a, and that's going to be the number we bring outside of the brackets. Okay, so we put it into this little equation here. So we know right away, and the second part of that is I'm going to do this in green. If we take that b again and just divide by 2, that's what will go in the brackets. Okay, so in other words, what we're saying here, I'm going to have negative 5, or in other words, this is going to be my, you could explain it as your h value. Okay, I'm going to take that 2. We know we're going to have x here, and we know it's going to be a negative, right? We would just take it, and this will be our h value. 2 divided by 2 gives us 1, so 1 goes in there. Okay? Very simple. We know we divide that by 2, that gives us that value. Now, what number to bring outside the bracket? That's this part here. Okay? So I'm going to rewrite that just below again, or actually I'll move this so we can see this. Okay, so our b term, it's a bit of mental math. B term is the negative 2, 2, squared. Now, this is the tricky part. It's technically times, and you know what? I'm going to rewrite this. I don't want it to be inside the brackets. I want the negative to be outside the brackets. Negative a. So times negative, what's that term there? Negative 5. So negative 5. I know it's a little confusing to do just alone in your head. But what would negative 2 divided by 2 be? Yeah, and what's 1, or, well, it'd be negative 1. What would negative 1 squared be? Yeah, just 1. So we have 1. And then times, what's negative 5 technically? Yeah, so times 5 gives us 5. So 5 is going to be the term that we're going to bring outside the brackets, and because it's positive, it's like doing plus 5 plus 35. So this is our plus 5, so we can jump ahead. With a couple side calculations, we can pretty much get to the end of completing the square. We end up with negative 5, x minus 1 squared plus 40. Okay. So this is a fast way to do it, but the side calculations are a little more complex. A lot of things you got to do in one step. So we'll recap quickly. I took this term here, and I said it was going to be our h term, right? Essentially what we're referring to here is our h term and our k term. Okay. So this is essentially, I don't know why I did it in the green color, it should really have been in the blue. This is how we find our h term. And this guy here is essentially how we find our k term. Okay, so we take the 2, we divide it by 2, it gives us our 1. So we bring down the negative sign, and it's just negative 1. That part's easy. The tough part is what term to bring outside. We take this b, and we divide it by 2. So negative 2 divided by 2 gives us 1, and technically squared still there, or negative 1, sorry. Negative 1 squared is positive 1. And we have to multiply by negative a. Well, in this case, a was negative 5, so it's negative times negative 5, which gives us positive 5. So we have our 1 times 5 gives us positive 5. So we bring positive 5 to the outside. Now, if that's too much to do in your head, that's fine, but it is a fast way. And when you do this often, you'll be able to do that in your head after a while. Okay, but that's just a very big shortcut in terms of side calculations. The second one might be the quickest one for you in terms of going through it. Okay, so we showed you how to turn standard into vertex form. Now we're going to find the inverse of a function. And we're going to find the inverse from our vertex form. We can technically find it from many ways, but from vertex form is an easy way to do it. Probably one of the best ways because there's only one x variable. In our standard form, we have x squared plus x. It gets complicated. And same with factored form, we'll have x minus 5, maybe x plus 2, something like that. There's 2 x's. So we want to work from vertex form because there's only one variable of x. Now, what does f of x stand for if we're going to graph? Do you remember?
Y.
Yeah, so really this is like saying if we're going to graph this, y is equal to 4x minus 3 squared minus 5. Okay. Now, this represents the normal function, and they'll use this f at power of -1x. That represents the inverse function. That's what we're trying to find. Okay. Now, what we want to do is when we're going to find the inverse, we take the x and the y, and we swap them in their place. So now we're left with x is equal to 4y minus 3 squared minus 5. The goal, again, is to isolate y once again. Okay. So when isolating a variable, when we simplify, we usually use bedmass. When we're isolating, we kind of use something called, you could call it reverse bedmass. So we're going to deal with what we normally deal with last in bedmass. So we have our brackets, exponents, division, multiplication together, and adding and subtracting together. Normally do with adding and subtracting last. We deal with them first. So I'm going to deal with my negative 5. When I move negative 5 to the other side of the equation, what is it going to become?
Positive.
Yeah, so I'm going to have x plus 5 is equal to 4y minus 3 squared. Yeah. I've done with all my adding and subtracting, so the next thing I deal with in a reverse bedmass is division multiplication. Now, the division multiplication, we have multiplication. 4 times this bracket. So I'm going to move that 4. How would I move it to the other side? Yeah, so we need to divide both sides by 4. So now I'm working with x plus 5 divided by 4 is equal to y minus 3 squared. Okay. Now the next step here is I have an exponent, so I'm going to deal with the exponent next. How do I move that exponent over? Yeah, in order to get rid of, or they say cancel out, but the opposite operation of a squared would be a square root, so we would square root both sides. So we're then left with the square root of x plus 5 divided by 4. Okay, x plus 5 divided by 4 is equal to y minus 3. Okay. And then finally, last thing I got to do is move that negative 3 over, right? Because we got rid of the brackets. So when negative 3 goes over, what does it become? Okay, but this time he's not underneath the root. It'll be x plus 5 divided by 4 plus 3, kind of outside of it, is equal to y. Now, when they represent a root, usually what they'll write in front of it, because technically when you find a square root of any number, like for example, let's do square root of 25. What are the square root of 25? Just 5?
Plus and minus.
Plus and minus. So sometimes what they'll do is they'll represent it like this, plus or minus. Okay. The reason and what they'll sometimes also do is they'll probably represent it, so we can say or y is equal to 3 plus or minus the root of x plus 5 divided by 4. Now the reason I want to leave it in this form is because this is much more similar to what we're used to seeing when we do our function. And again, this is the inverse, right? This is 1x is equal to. Now normally you don't write 2 equals 2's here, but we know that y is the inverse for this. Okay, so our inverse function of the original is that. The reason I left it this way is just so we can kind of compare it to when we write a function f at x is equal to the function minus plus k. So we can write it like this. So we can see what our a is, our k is, our c, and our d. You remember doing those and how to remove this? These transformations, when graphing, they work for any function. The f essentially represents a function. So it could be a quadratic, squared, or it could be a root function. Whatever these letters are, they'll do the same thing to every function, just the shape of the function is going to be different. So in this one, this 3, if I'd written it this way, the 3 could be deceiving to what letter it is. But when I write it behind the rest of the equation, which letter do you think it represents?
Sorry.
So the 3 here, in terms of these 4 letters, these 4 variables, when I write it at the end of the equation, which letter do you think it represents? D, that's right. That's why I've written it this way. Now your book sometimes will write it this way with the number in front, but I write it at the back so that it's easy to tell that this is our D. So it's going to move the root, okay, up and down. Okay. In here, the k function is a little harder to find. It would have been nice if we found a nice one, because I have to actually factor out the 4th. And then this number is going to change to 5 over 4. Oops. 5 over 4. Oh, no. Sorry. He's going to change to just 5. Oh, he'll be easy to work with. If I put him in factored form, so this is like factoring, okay? What I'm going to do is I'm going to take out the 1/4, okay? And when I take out the 1/4, what's going to go underneath or inside those brackets, we'll write it another time here. So we get plus or minus the root of, just so we can see the k, a 4th times x plus 5 plus 3. The reason I do it this way, okay, so we know that's our d. What's our k value?
4.
Well, a 4th, right? 1 over 4, right? And we do it that, yeah, well, we put it to the outside, because this actually means divided by 4, or times a fraction of a 4.
When you graph it, I thought you changed it.
Oh, you're right. We definitely would go like that. So in the end, we'd invert it, and you'd be horizontal, stretched by a factor of 4. You're exactly right when we go to do that. And what will my c value be? There we go. Right? That's my c value. And we don't really, our a value would be here, kind of thing, multiplied by. But we don't really have one, so you could say it's like multiplied by 1 in this case. Okay? So our a value is kind of like a 1. Let's put it up. Okay, the reason they write it this way, and we'll
because then that just looks like it's A, not
yeah, it really does look like it's A. But because it's plus or minus, a is multiplied by the function. So technically the a value is here. The root is the function, or if it's a quadratic, the brackets are there, and the squared is the function, and the a is right outside to be distributed in. Just like the 1 here, whatever happens here would be distributed in at the end. You could almost think of it like it's in brackets. Okay? Now when it's plus or minus, that's more of a d value. D is plus whatever this function times a is going to be. It's almost like the last thing you would equate in terms of that math. Okay? So they'll put it in front just so they can put the plus or minus into the equation, because normally they don't start the equation with that. But it would still be the d value. It would move this up and down. Or, well, in this case, up. So in this case, up. Okay, I'm just going to quickly go over graphing a parabola. So if you recall, when we graph parabola, our original starts here. We go over 1, up 1 for the points, right? And we go over 2, up 4. So these are coordinates of an original parabola. 2 and 4, 1 and 1. Is this familiar to you? Yeah, okay. So we have that stuff. We'll clear that off now. Now, in our equation, actually, our equation read, I think it was f at x our original equation was f at x, what we put into our vertex form. It was 4. I guess we're going to have to bring it up. Sorry, give me 1 second. Go back up to the original guy and look at the whole page here. Okay, so it was 4 minus 3 minus 5, so that's how we remember it, okay? So, our original equation was f at x. Our a value was 4, x minus 3 squared minus 5, okay? So 4 gives us vertical stretch because it's an a value that's greater than 1. So we're going to plug that guy in, and we'll do each at a time. So the first equation I'll plug in is 4x squared, so that we'll see a stretch. That's going to go over here. Then the next one we'll do is 4x minus 3 squared, so we can see what a horizontal shift looks like. And then finally we'll put in 4x minus 3 squared minus 5 so we can see a vertical shift. Okay, so all these numbers are about to disappear. So let's put them in. So I put this into the equation 4x squared. Okay, and if you notice, the parabola now has stretched. Where normally we're at 1 and 1, I go over 1 up 4. 1, 2, 3, 4. There's our first unit. When we go over 2 up 4, it's at way up at 16, right? Way up there. So we have it's been vertically stretched or squished in. It looks thinner in this case, right? The next thing we would do, same idea is 4 bracket x minus 3 2. Okay, so in the next one what we have is that red shape has now shifted 1, 2, 3 units to the right in a positive direction, even though it was a negative. Remember, because we said that it is counterintuitive when we're doing that stuff. It goes the other way. So this parabola is shifted 3 to the right. And then finally, the last one we're going to do is we're going to add the 5 in. So 4x minus 3 squared. What do we say? Minus 5, right? There we go. So what happens there is our green one has now shifted 5 units down. 1, 2, 3, 4, 5. So here is our parabola at the purplish fuchsia color. That's what our function is. Okay. So I'm going to turn the other ones off just to make this a little cleaner. Okay. Can I do that from here? I'm going to just close him, close him, close him. Now this is where our function is. Now we knew that our inverse looked a little different. We're going to write what our inverse was again. It was x plus 5 divided by 4 plus 3. Okay. So we had our inverse function was plus or minus the square root of x plus 5 divided by 4 plus 3, right? So we don't really have an a in that one, but that's okay. We're going to show you what an original root one looks like. So the first one I'm going to show you is essentially an f at x is equal to root x to show you what the original parabola is. So we'll type that in. Then the next one we'll do is we'll talk about a k shift. Remember how we factored this? We made it a fourth x plus 5 underneath the root. So this is our k value. So what I'm going to do is after I show you the first guy, we're going to do f at x is equal to root 1/4 x. Okay, just to show you a horizontal stretch. Then we're going to do f at x is equal to root 1/4 then x plus 5, so that we can see a horizontal shift. And then the last one we'll do is f at x is equal to root 1/4 x plus 5 plus 3, so we can see a vertical shift. So all these numbers are about to disappear, but this way we can kind of remember what we were doing. So the first one we're going to do is root x to start with. So x. Okay, so there's our first one. Okay, so this is what a root function looks like. It's kind of, now normally it would kind of look like this, a sideways parabola, but because this program only graphs functions, a rule with functions is if we draw a vertical line, it can only cross a point once to be a real function. So they don't show the bottom part of the parabola, okay? And I don't know if your teacher will want you to do it or not, but it's fine. Okay, so here's our root function here. Now we said the next one we were going to do is the same idea, but the only difference this time is we were going to do 1/4 x, right? So now what's happened is we have a horizontal stretch. Remember, we multiply our x value. So this point here is 1 and 1. Because our k is 1/4, we always multiply by 1 over k, which is essentially what? Just the number 4, right? So we multiply the x value by 4. So I know the next point along here is 4 times 1 is going to be 4n1. And if we take a look, we're at 1, 2, 3, 4. Oops. 1, 2, 3, 4. There it is. 4 and 1 is the next point on the fuchsia line. Okay, so we've had a horizontal stretch. That was our k effect of it. So it's become, our old root looked like this. Our new one is kind of looks like it's smaller, thinner one. And if it was to completely pan out, it would be like this, thinner on the inside. Okay. The next thing we said we were going to do, we were going to put 4 and bracket x plus 5. That was the number? Yeah, I think it was plus 5. Okay. So now if we take a look at it, that plus 5, remember that was like a c value. So it goes from our blue one, it's gone 1, 2, 3, 4, 5 units to the left in a negative direction because it's a positive number. So we've gone from the fuchsia looking one to the purple looking one. The entire root has shifted 5 units to the left. Does that make sense? Mm-hmm. Okay, and then the last one we did, same guy, square root. Yeah. Oh, okay. Yeah, it's this one. Thanks. 1/4 x plus 5. What was the last number? Do you remember? Let's just make it up. It doesn't really matter, right? Oh no, I do remember. It was a 3.
Well, it's 3 in that one.
Yeah.
Would it be 3?
Positive 3. I'm quite sure that's it. There we go. So we have our final one here. So from the purple guy, we've moved up 1, 2, 3 units. It's gone 3 units up. So this is our inverse function. Now I'm going to get rid of all of our steps. Really, our last one here is kind of like that. That's the shape we're looking for, right? So I'm going to get rid of the other ones. So we're just left with our inverse function and the original function, okay? So this is our inverse function here. And our fuchsia-looking one is our original one. Now an inverse, when you graph them, it's actually being flipped on a, actually I'm going to just put the point here. So like it's easy for me to see. And then, okay. What another way you can describe it is it's like it's been flipped on a 45-degree angle. Okay. So from our original purple one, when we were doing flips with a piece of paper, if you were to fold this paper in half over here, what you would get is this guy here. This is what the inverse is. So instead of flipping directly on the x-axis or directly on the y, this one flips on a 45-degree angle. And that's why it looks the way it does. Okay? So that's why an inverse graph looks like that compared to our fuchsia one.